equation. Yes. Yeah. Okay. So, right, should be so note. So I have a note that they have given the answer which is close to zero, but not exactly. That is different between what we call mathematics and computational calculation. Okay, so that the last example of uniform distribution. This is the easiest distribution for continuous random distribution. Next is what we're going to spend most of our time working on, which is normal distribution. Any question about uniform distribution? Okay, let's see normal distribution. Normal distribution is the most important of all probability distribution. Right? We learned about it a lot. The function of normal distribution is given by this. Right? So the probability density function is 1 over sigma, right? Sigma multiplied with the square root of 2 pi, and then multiply with exponent base e to the power of 1 minus 1 over 2, and then y minus mu divided by, again, sigma, everything squared. And the value of y can be from minus infinity to plus infinity. And obviously, this is very difficult. It's very difficult function to work with. And but luckily, we don't have to do integration with that function because it's going to be a painful job to do that. We can use table or the R program to calculate instead. Okay, so this is another, sometimes, this is the correct form, like e to the power of this, but some people think that it's quite difficult to write down, so they use, instead of using base e to the power, they change to exp, right? And then they move the power down a little bit, the exponent down a little bit, so that everything is in the same line, but it's still the same function. Okay. The correct form is this. It's always like e to the power of something. The graph look like this, right? Symmetrical around the means, which means that the left, right, we split that in the middle, and that middle is center at the mean, the expectation, or mu, and the left and the right hand side is the same, exactly the same, symmetrical. So because the area under the curve have to be 1, so when you split 1 in half, it means that the left hand side is 0.5 and the right hand side is also 0.5. Okay, I showed you this before, right? It's the old diagonal, and you can see that the formula that we just show it in this banknote. And for better or worse, this is a guy that come up with that formula. The reason why we use normal distribution a lot, because most of the time, statistics that we use are like, if you go out in the world, you collect data and you calculate some index from the data, they're likely to have a normal distribution. So that's why it's called normal, because it's happening a lot. I think I mentioned it before. In statistics, sometimes statisticians don't call it normal distribution; they call it Gaussian distribution. And it's Gaussian because the name of this guy, Carl Friedrich Gauss. So it's the distribution of Gauss. If you like reading the biography about a genius, you can try to read Gauss. His biography. He is a certified genius. Okay. So yes, you can see, right? in our normal distribution function, there are two parameters that you have to, that you need to know before you can calculate any probability, right? So one is the standard deviation, right, or the square root of the variance, and the other is mu, the mean of the expectation of y of the functions. Pi, we know pi, right? Pi is a constant value. E as well, the base E has a constant value. So the only thing that we don't know is just the mu and the sigma or standard deviation. So if we know these two parameters, we can calculate the probability of y for any values. Okay. Unlike the range of uniform distribution where we have the limit, right, the minimum and maximum, the normal distribution range from minus infinity to plus infinity. Okay. So a normal distribution, when the mean is 0 and the standard deviation is 1, have a special name. It's called standard normal distribution. So you can see that I replace, right, now the standard deviation is 1. So I put a 1 here. And mu is 0. So when we place that into the formula, we got this. So it's a simpler form. This is when it's a normal distribution with mean 0 and variance of 1. Okay. So when standard deviation is 1, 1 square is 1. So it means that the variance and standard deviation is the same, is 1. And we call it standard normal. And that is the reason why it's very important. Okay, as we shall see shortly, any normal distribution can be converted to standard normal distribution with simple algebra. This makes calculation much easier. Okay, so if you open the PDF file of statistic table I give you, right? You can see that, okay, I'll go back to the top, right? So first, we have binomial table, and you can see that in the binomial table, you have one parameter, which is the probability of success, right? So you have to identify the probability of success, and I said you have two, is P and N. So we have like the first table here is when n equal to 5, this is n equal to 10, and you have to look for P. So you can see that within one distribution, you have more than one table, right? It's the same with Poisson. Is it Poisson? Okay, so that for Poisson is the same. In Poisson, you have lambda, so you have to identify lambda, and then you can calculate the probability of y, right? So again, one table, but there are many value of parameter. Okay, so that's the Poisson, right? A lot of table, but you can see that for normal, you only have one. Okay, so for normal distribution, you have only one table, and that's enough. And this one table, right? You can see that it's gonna say standard normal. So the mean is 0. You can see that 0 in the middle, right? And the variance and standard deviation is 1. So as we say that normal distribution can have different mean, right? Mean can be any number, 1.5, 3, 10, 100. Variance as well can be any real number. But we don't have table for a specific mean or specific variance. We have just one table for mean of 0 and the variance or standard deviation of 1. The reason is because no matter what mean or variance you have, you can convert that into standard normal. So that's why you need only one table, right? Next, what I'm gonna tell you is that first, why the conversion makes sense. How can we convert like random variable normal distribution with any mean and variance to mean 0 and variance of 1. And second, I'm going to tell you how we can read that from table. Because why we need table? Because if we don't use this table, you have to integrate that function. And you can see the function is very complicated. If we will try to integrate that, it's going to be a lot of job. So it's better to use table like this or use the R command to calculate the probability of a normal distribution. Okay, so let's see. Okay, so the first parameter that we focus on is the mean, right? What is the mean? The mean is tell you where the middle of the distribution is, and if you move the mean, right, you're gonna move the distribution left or right. Okay. So as you can see here, right, so we have the black line is when mean is 0, the blue is mean is 1, and the green line is when mean is 2. So you can see that if you change the mean, you don't change the shape of the distribution, you don't change the variance. What you change is that you shift left or right if you're reducing the mean, right? So it means that you're gonna move the whole thing to the left hand side. If you increase the mean, you're gonna move to the right hand side, but it will not change the shape or anything. Sometimes mean is called a location parameter because it's moved the location of the whole distribution. Okay. What about the variance or the standard deviation? So this telling you how flatten the curve or how varies of the value of our distributions. So you can see that for the black line, right? So this is when standard deviation is 1. So you can see that the fact that we have this shape is mean that most of the value is moving around here, right? The value that likely to happen is move between here and here. Now when you become like the blue line, the standard deviation is smaller, 1/2. So you can see that the range of possible value is shorter, right? The variance is smaller, so it means that the shape is shorter. And the green line is when the standard deviation is 3, or the variance will be 3 square or 9. You can see that now the value of your y can move in a big range, right? Can anyone tell me why? When you have a big variance, your distribution have to be shorter. But when you have small variance, your distribution have to be higher. Can it just stay the same height and just increase the variance? Can anyone give me the explanation? So the only condition that you have for the shape of the distribution is that the area under the curve have to be 1, right? So if your variance is smaller, so when I say like the area under the curve have to be 1, it means that the area under the curve of the blue line, the black line, the green line have to be 1. So they must have the same area. Right? In other words, you think about if you have a clay, right? A clay or dinaman, right? And you have the volume of the clay that you have is just 1. So when you try to make it become like very small in terms of variance, it means that the rest of the mass have to shoot up there in order to remain the same volume of clay. On the other hand, when you're spreading your clay around, because you're spreading around a lot, you don't have enough clay to be on the top, right? So these 3 graphs, it show you that the distribution that have the same mass, which is 1. So when you become, the variance increase, it has to be shorter. Because if it's not shorter, right? If we have this big variance, but still we have the same height as the black one, it means that the volume of the area have to exceed 1. So when you limit with that area of 1, you're going to have a shape like that. But you can see the difference between the variance and the mean is that when you change the variance and you fix the same mean, you don't move anywhere. You're just making like the flatten of your curve if you increase the variance, or you sort of like make your curve become higher if you shorten the variance. So it changes the shape of the distribution, but not the location. Okay? So we can use the following function to convert any normal distribution with any mean or any variance to the standard normal. Okay. First, okay, you can see that the function or the formulation that I'm gonna use is this one, right? Y can have any mean or any variance or standard deviation. What we have to do is that we subtract the mean of y, and divide it by the standard deviation of y, and then you will get z, where z have a standard normal distribution. So the way we can convert any normal distribution to be standard normal is to subtract its mean and divide it by its standard deviation. Okay, I can show you. Let me, I think I have. Okay. Okay, let me check. I think I have. Okay. I'll show in a minute. Okay, let's do this first. Okay. Okay. So this graph, right, means that the blue is y, right? The blue is y. The blue can have any mean. We don't say what mean it is or standard deviation. It can be any number. If you subtract the mean and divide it by standard deviation, it's gonna convert to mean of 0 and a standard deviation of 1 or variance of 1. Okay. Why? Is because when you subtract the mean, right? When you subtract the mean, okay, what you do is you move, right? So let's say that this have a mean of 4. When you subtract the mean of 4, what you do is like you move the whole distribution to the left. To where? You move to where the mean becomes 0. Okay, so if you have a positive means, it means that you subtract the mean, then the whole distribution will move to the left to 0. If you have a negative mu, and then by minus the mean, it means that you actually plus, right? Because you minus a negative mean, so you plus it. So you can move the whole distribution to the right hand side where its center at 0. And when you divide it by standard deviation, right? So this is going to change the variance, right? You're going to change the variance from any number here to become standard deviation of 1 and variance of 1. Okay. I can show you using okay. So okay, let me okay. So we start with x. Okay, the histogram of x. You can see that the mean of x is definitely not 0, and you can see that it varies a lot, like from 20 to 40. So the variance, standard deviation, is certainly not 1. And you can see here, the way I generate x is that I want x to be normal distribution, R-norm, right? Observation is 1000, and the mean is 30, and the standard deviation is actually 4. Okay, so that's how I generate x. Now, after I subtract x, you can see that the mean here becomes 0, right? We change from 30 here to 0. But the variance is still big, because you can see that, okay, so the value of x is about 20 to 40, right? Most of the mass of the probability is between 20 and 40. So you can see that the length here is about 20 units, okay? So when I subtract only a constant, 30, I change the location so the mean becomes 0, but the variance is not, right? The variance is between minus 10 to 10. So that again, the length about 20. But now, if we divide it by the standard deviation of x, which is 4, you can see now that not only the mean is at 0, but now it varies between most of the probability between minus 3 and 3. And that is a variance of 1. You can see that even though x, right, we started off x with mean of 30 and standard deviation of 4, when I subtract the mean of 30 divided by the standard deviation of 4, and I define a new variable z, the mean of z is something close to 0, and the standard deviation of z is something close to 1. Okay, so we have only the standard normal table because we can change any mean, any normal distribution with any mean or any standard deviation to be the mean of 0 and the variance of 1 by doing standardized. In fact, it doesn't have to be normal distribution. Any distribution, if you subtract the mean and divide it by standard deviation, it's going to have mean of 0, the variance of 1. And the distribution remains the same. If you start off with, say, a Poisson, okay, probably any distribution, even uniform, right? If you start with mean of something, variance of something, subtract the mean divided by standard deviation, it's going to have mean of 0, the variance of 1. And the distribution going to be going to remain the same. Any question for this graph? Sorry. Any question? Okay. And now, let me tell you the mathematical explanation of why that is the case. And this is the reason why when I'm teaching you expectation and variance operator, I have to explain in details of why expectation of C is equal to C expectation of X plus C's expectation of X plus C is because of this. Okay, let me explain. So now we suppose that x, right, have the mean of x is 30 and sigma standard deviation is 4. So similar to what we have in the example, right? And we generate that by using x minus the constant of 30 and divided by standard deviation. And I can prove to you that expectation of that is 0 and the variance of that is 1. Okay? So expectation of that is the expectation of the whole thing, right? X minus 30, everything divided by 4. Now, to make life easier, I'm gonna say that we have two terms. We have x over 4 minus 30 over 4. Okay? I'm doing this because it's easier to have two terms because this term is a constant. This term is a constant multiplied with x, right? According to our expectation, we can take expectation inside if you have plus or minus here. So you have expectation of x over 4 minus the expectation of 30 divided by 4. Now, the expectation of a random variable multiplied with 1 over 4, you can take the constant 1 over 4 outside, you can have 1 over 4 expectation of x, and then minus with the expectation of a constant is a constant itself. So we have 30 divided by 4, right? What is expectation of x? Expectation of x is 30, right? So it means the front is 30 over 4 minus 30 over 4. So 0. Okay? What about the variance? The variance, so bear in mind that z is continuous random variable. When we learn about expectation and the variance, we learn in discrete random variable, but it's the same. Okay, just some replacing with expectation, but behavior is the same. So the variance z again is the variance of a short term x minus 30 divided by 4, or x over 4 minus 30 over 4. Okay, so you can see that now we have the variance of a random variable minus a constant c. So if you remember the form, the properties of the variance is that when you have the variance of a random variable plus or minus a constant, we can get rid of that. Okay, so c is gonna disappear and equal to the variance of x over 4. Now we can take the constant 1 over 4 to be in front of the variance operator, but you have to square it, right? I proved to you, you have to square it. So it's going to be 1 over 4 squared, and inside is the variance of x. Now, what is the variance of x? The variance of x is standard deviation squared. So it's 4 squared, right? Now we have 1 over 4, everything squared, but 1 squared is 1, 4 squared is 4 squared, so we have 1 over 4 squared. So you can see that that cancels out, and we have 1. Okay? So we can prove from the properties of expectation and variance that we learned that when you use this formula, x, right, minus the mean divided by standard deviation, you're going to have expectation of 0 and the variance of 1, right? The variance of 1 means that the standard deviation of that is also 1, right? Because 1 squared is 1. And you can see that that doesn't have to be normal, okay? This can have any distribution. I can generate you like using exponential distribution to generate x. But as long as I know the mean and the standard deviation, I can subtract the mean divided by standard deviation, and I guarantee you that the outcome gonna have mean of 0 and the variance of 1. But we don't have time for that because we have a lot of things to cover. Okay, any question? No? Question? Sorry, that have to be minus. It have to be minus here. Sorry about that. Okay, I'm a little bit stupid now. So that should be x, right? Sorry, a lot of mistakes here. 16 squared. Okay, that's correct. I'm sorry. That equality, yeah. Okay. Sorry. Okay. So next, okay, an example. Suppose that another gas station now, we believe that the daily demand have normal distribution, right, with mean of 1,000 and standard deviation of 100 gallons. So the station manager has opened the station for business and know that there are exactly 1,001 gallons of regular gasoline in storage. Now the problem is the next delivery gonna be later today at the close of the business. So it means that today he only have 1,001 gallon to sell. Now he want to know what is the probability that he will have enough regular gasoline to sell, right? So he wonder whether is that gonna be enough for today, right? What is the probability that the sale today will be less than what he have, which is 1,100 gallons. So, since the demand is normally distributed with that mean and standard deviation, what we want to find is, we want to find the probability that Y gonna be less than 1,100. Okay, that is what we want to find. Now, if we were to have to integrate, then we have to integrate that normal PDF functions from minus infinity up to 1,100, and that's gonna be a lot of work, right? So it's better to complicate it, right? So it's better to convert Y into Z, and then we can use the table we have to read off the probability that Y going to be less than 1,100 gallons. Okay, so this is a graphical representation of what we want, right? We know that the demand is normal distribution with a mean of 1,000, and we only have 1,100. So what is the probability that the demand will not exceed 1,100? Okay. So I'm going to explain to you how we can. Okay, let me write it down, right? Because it's easier to digest that way. So what do we want? We want Y, probably a Y less than 1,100. This is what we want, okay? But if we calculate from Y, we have to integrate the normal PDF with mean equal to 1,000 and the SD of 100. So we don't want to do that. So what we want is we can change y from mean 1000 and SD of 100 to mean 0 and SD of 1. So what we do is we know that we have to use the formula y minus the mean, right? 1000 and divided by an SD of 100. But so you can look at this like it's not equation, right? Because it's not equality. We have less than or equal to, but still it works like equation because we want to keep that. We want to keep that less than or equal to. So on the other side, you have 1000 and 100. So what you do to y, you do to 1000 and 100 to keep the balance between two sides of the equations. So you have to minus 1000 on this side as well and divided by 100. Okay? The probability statement in outside is still the same. Now, y minus the mean divided by SD, it will become SAT or standard normal distribution. However, 1100 minus 1000 is 100. 100 divided by 100 is just 1. So we now translate or converting from this probability statement to that probability statement. So if you want to find the probability of y less than 1100, it will be the same. Okay? I emphasize the word that the same with the probability of z less than 1. Okay. So next, I'm going to teach you how to calculate that, or maybe to look for the probability of z less than 1 from the table. Okay, but before that, let me explain why. So basically, what we do is like this. Okay, you can see. Okay, so the bottom, right? The bottom is the normal distribution of y. You can see that the mean is 1000, right? So I equivalent that to the top, which is standard normal of mean 0. So you can see that what we do is like, okay, so in the world of, so this is like multiverse, right? If you like the Marvel movies. So in the world Y, the mean is 1000, and we want to find the probability of less than 1000 and 100. But in the world of Z, you can see the mean is 0 and 1000 and 100 is 1. So the area here and area here will be the same. Okay, because in any worlds, the area under the curve have to be 1. Right? So what we do is just like we scale. We scale from mean of 1000 and the point of 1100 to the mean of 0, and 1100 happen to be 1. So if I look for the table of standard normal of the probability of less than 1, that will be my answer, and that will be the same as the probability of y less than 1100. Okay, so that we have to use table 4 in our handout, and this is table 4. Okay, the bad thing about table 4 is that table 4 doesn't tell us the area on the left. The table 4 tells us the area on the right hand side. But that's okay, right? Because you know that the whole area under the curve is 1. So if you want to find the white area, right, you just subtract the shaded area to 1 and then you get it. So let's see. So I want Z to be 1, Okay, so you can see that it have on the top it have the second decimal of that, second decimal place of that, but the first decimal is here. So you want that to be 1. So 1, right? The second decimal is 0 and 0. So that is 0.1587. But 0.1587 is the area to the right. So if you want the area to the left, you have to subtract this number to 1, and then you get the y area. Okay, I hope that's simple enough. So let okay. So from the table, right? The probability of z greater than 1 is 0.1587. So if you want the probability of z less than 1, you subtract that from 1, you get 0.8413. I told you that 0 is the mean, right? So the left hand side of 0 is going to be 0.5. So when you have this area like this, it's going to be more than 0.5. And you can see that from the answer is 0.8413. So there is 84.13% chance that you can sell, you have enough gasoline to sell. So the demand will not exceed 1,100 gallons that you have. Okay, so this is when in using R function. So R function for normal distribution is norm, NORM, but we're gonna calculate a cumulative or probability distribution. So we use P norm, right? P norm, we want Z to be 1, mean to be 0, SD to be 1, and you want lower tail, well, we want lower tail to be true because we want from 1, we want to calculate the area from 1 to the left hand side. So we want to calculate from the lower tail. So the lower tail has to be true, and you can see that it gives me exactly the number that I have here. Okay? If you say that the lower tail to be false, so it's going to calculate from 1 to the right hand side to the upper tail. So you can see that it's going to give you the same number that you get from table 4 in the PDF table that I gave you. Okay. In the final exam, you're going to have the same table in the final exam, right? Exactly the same table. So you can have a look at that table. You don't have to bring it to the final exam. It's going to be reproduced with the final exam. If depends on whether I'm going to have normal distribution, t-distribution, chi-square, f, or everything. Okay? Any question? Okay. Now, another example, right? Consider an investment when return is normally distributed with a mean of 10% and a standard deviation of 5%. Now, first, determine the probability of losing money. So, another word, determine the probability of negative return. Right? B, find the probability of, again, losing money if increase the standard deviation to 10%. Okay. Let's do the first question. So the investment losing money when the return is negative. So basically, when you're asking the first question, determine the probability of losing money, it means that we want the probability of y less than 0. So y is a random variable, and the mean of y is 10% right here, right? The mean of y is 10%, and we want the probability of y less than 0. Okay. So again, we want the probability of y less than 0, but if we don't want to integrate the PDF functions of normal, distribution, then we have to convert it to Z, the standard normal. So what we do is we subtract the mean divided by standard deviation. Here, both sides of the equation have to subtract mean of 10 and divided by 5. Y minus mu divided by standard deviation is Z. So 10, right? 0 minus 10 divided by 5 is a negative 2. So the probability of y less than 0 is the same as the probability of Z less than negative 2. Okay, that is important. Why? If you look at the table for the Z table, you can see that we don't have a negative value. This is only positive value, right? You can see that we don't have a negative value. So how can we find negative value? Because normal distribution is symmetric, right? The left hand side and the right hand side is the same. So we don't need a negative table because we can calculate the probability less than negative value using the positive one. Right? So let me show you why. How? Sorry. Let me show you how. Okay, so in this question, we want the probability of y less than 0, and we already say that equivalent to the probability of z less than minus 2. Okay, now if I draw the graph of z, okay, this is z, so mean is 0, so negative 2 is here, minus 2. So what you want is the probability of z less than negative 2. So you want this area. Okay? Now, because the distribution is symmetric, so it means the left and the right is the same. Now, instead of minus 2, what you can do is 2, okay, and then you can see, okay? So this area will be the same size as this area here because of symmetry. So that's why whatever you want to find on the negative side, right? You can find the same thing as the positive side and then you flip it. Okay? So let me give you an example. Let's say that what you want to find is the blue area here. Okay? So the blue area will be equal to the black area. And to calculate the black area, it's going to equal to 0.5 because half of the mass is 0.5, right? Minus the green area. And you know that in our table, it's going to tell you the green area because in our table, it tells the upper tail giving the set values. So you can calculate the red by calculate the green area. So in this case, I can tell you that the probability of z less than minus 2 can be the same as the probability of z greater than 2. It will be the same. Z greater than 2 is the green area. Z less than negative 2 is the red area. And the green area we can read off the table. Okay, so let's see. So let's look our table, and because we want the red area, right? We have to find the green area. So let's look for the green area in our table. So in our table, we only tell the upper tail, right? So you want the upper tail when z is 2. So you go down, and you see that 2, when z is 2, the area from 2 to the upper tail is 0.0228. Okay? So that is your answers, 0.0228. So that will be the probability of less than negative 2, same as the probability of z greater than positive 2 as well. So 0.228. And you can see here, okay? So the probability of, again I find other mistakes. So it have to be, sorry, but it have to be less than, okay? Here have to be less than negative 2 is equal to the probability of greater than positive 2, and it have to be 0.0228, and that is therefore the probability of losing money is 2%, 0.28 or 0.0228. Again, you can use, right, you can see that I'm using p-norm, right? So you can see that this in the first command, let me enlarge it. In the first command, because I don't have to convert to z, I can just use the p-norm to calculate the probability of y less than 0, right? When mean is 10 and standard deviation is 5. Make sure that the lower tail have to be true because we want the probability less than 0. So you can see that the answer is 0.02275. When you round it up, it's 0.0228. The second line is when I'm using negative 2. Right? So this is the probability of less than z, less than negative 2 because the mean is 0, SD is 1. Again, lower tail have to be true, and you can see that it's the same number, right? So whether it's y or z, the mean doesn't have to be the same, but if it equivalents, then the probability is the same. Here, I calculate now the probability of z more than 2, because now lower tail to be false, so I want upper tail, so I want the probability of z greater than 2. So I want the same thing that it show in the table, and you can see that it's the same, 0.02275. So if you know how to use R, then you don't have to convert at all. You can just type in what is the mean, what is the SD, do you want less than or equal to what, and then you specify the lower dot tail to be true or false, and you can get this correct answers here. Any question so far? Okay. Now the second question is that what will happen if we increase the standard deviation to 10? Okay, guys, so let's think about it. Okay? Okay, think for a second. See whether we can guess the answer correctly or not. Okay? So We know that when the standard deviation is 5, remember standard deviation is about the variance, right? Is 5, the probability of losing money is 2%, about 2%. If the variance or the SD now increase to 10, so you have higher, like more bigger variance, what do you think the probability of losing money? Is it going to be more than 2% or less than 2%? If you increase the variance, what do you think? So this is the same, like how we model risk in the finance market, right? Risk means higher variance. If we say that the stock market is risky, so it means that higher variance, so you can get big, return big, or you can losing big as well, right? So the situation when the SD increase from 5% to 10% is equivalent to higher risk. So you have a probability of now be more negative and be more positive as well, okay? So if we were to draw a graph, it will be something like this, okay? So we said that the mean is still at 10%. Okay. So at the beginning, in the first question, let's say that the variance is about this. So the 0% is here, right? And we say that the probability of losing money is about 2%, right? If you increase the variance, don't forget that when you increase the variance, the peak of the volume of the probability has to step down as well. So you can see from this that, okay, when you increase the variance, the probability of less than 0 should increase more than 2%, right? But what happened on the other side? You can see that now, let's say that this is 20%, right? Before, the probability of hitting 20% is small, but when the market become bigger variance, then it means that hitting 20% is become higher probability as well. So when the variance increase, not only you can have higher probability of losing, you have higher probability of making a lot of money as well. But it's more risk, right? Okay, so that is what I call intuition. Intuition is mean that you understanding. You don't have to work the math, but if you understand how this is all working, then you can guess what the answer will be, and let's see whether we are correct or not. Okay, so let's work out the number. So now the SD have to be 10, right? So now you can see that the probability of losing money is not SAT less than -2 anymore, but SAT less than -1 because we have bigger SD. Okay, so that would be equivalent to the probability of SAT greater than 1, right? So if you go SAT greater than 1, you can see that it is 0.1587, and you can see that here, right? So I already 0.1587. So you can see that when the standard deviation is 5, the probability of losing money is only 2%. But when the SD is 10%, then the probability of losing money increased from 2% to 15.87, or almost 16%. So our intuition is correct. Increasing SD, making higher probability of losing money, but at the same time, it also increasing the probability of earn a lot of money as well, according to the graphical representation that I just showed you. Okay, so here investment become riskier. So using the same thing, right? So this is when we want the probability of less than 0, mean of 10, SE is 10. You can see that is 15.86%. Right? If you change it into Z mean 0, variance, SD of 1, so you have to put negative 1 here, you get the same number, lower tail to be true. But if you want the upper tail, equivalent is positive 1, and the lower tail to be false, then you get the same answer as well. Any question? Okay. So that is almost the end, but not. Okay. So that is how you calculate the normal probability distribution using standard normal distribution. Now, sometimes we also interested in the opposite thing, right? So far, we calculate the set in order to calculate the probability here, right? But sometimes it could be the case that you know the probability, but you want to know what set corresponding to that probability. Okay. So this is the reverse case. When I give you a probability and you give me, you return me the set. Okay. So giving the area under the curve, what is the corresponding value of ZA here? That gives us this area. Always like area at the upper tail. Okay. So if area A is, for example, if area A is 2.5% or 0.025, it means the white area is 0.9750. So, or in other words, the white area is 97.5, this area is 2.5. Add them up is 1. Okay. So, what the value set corresponding to the area under the curve of 2.5%? Right? Let's say that we want. What you do is like we have to do reverse lookup on table 4 for 0.025. Okay, let's go. Let's do that. So far, we calculate the set and we read the probability in the table to be our answers. But now what they want is they want the area to be. Okay. Oops. No, sorry. Okay. So they want the area to be this area to be 2.5%, but they want you to find the set that corresponding to the probability in this area of 2.5%. So what you have to do is sort of reverse lookup, right? So we have to look in the table for the probability of 2.5%. Okay. So I have to go down because this is just 7%. I have to keep going. Okay, so that is 2%, 2.07%. So I want 2.5. So it should be here, right? So you can see that this is the probability of that area of 2.5%, and the corresponding set is gonna be 1.9, okay, and then for the second decimal place, right, I have to go up, so it's 1.96. So the question can ask you in this way as well. Give you the probability and find me the set that corresponding to that probability to be the upper tail of the distribution. So here, if the area is 2.5%, then the Z value is 1.96. And you can see here is 1.96. Okay? Is the reverse lookup of the table. Or, okay, we can use the Q norm. Okay, if you type R and then normal distribution, okay, and look at this, okay, so you can see that, right? When you have a normal distribution, you have D norm, P norm, Q norm, and R norm. We already use D norm, we already use P norm, we already use R norm to generate normal distribution. Now the last one is a Q norm. This is the one that we're using here. So basically now we have been using all the 4 variations of the normal distribution command in R. Actually, for any distribution, it can have D version, P version, Q version, and R version. Right? R is for generating a sample that have normal distribution. D is to calculate the density specific value. P is for interval. Q is what we're doing now. Q is when you give them the probability, and R will return you the Z values. So you can see that here, what I'm doing is that I use Q norm and I give them 0.025, 2.5%. This is the standard normal, so mean is 0, SD is 1. I want lower tail to be false because I want the upper tail, because in the picture it's upper tail, and you can see they give me 1.959964. You round it up to 2 decimal place is 1.96. Okay? If you specify the same 2.5%, but you want lower tail to be true, so you want the 2.5 at the lower tail of the distribution, that will be minus 1.96. Are we surprising? No, because we know that Z distribution have symmetric. So if on the positive side, this is 1.96, negative side will be minus 1.96. Okay? And if you have, again, instead of 0.025, 2.5%, we get 97.5, right? Why I'm using this number? 97.5 plus 2.5 is 1, okay? So this is when we give 0.975. Again, mean is 0, variance 1, lower tail to be false. So we want the upper tail, right? The upper tail, but we want the upper tail to have the area of 97.5%. So it gives us minus 1.96, right? Because when you have upper tail to be 97.5, what you have left on the lower tail is only 2.5. The same thing is here, right? So it depends on what you give them. You're gonna get similar answers in this situation. Okay, so why are we interested? So I have 2 slides left. Okay, I think we have 1 minute, so don't worry, we can finish it. Okay. Why are we interested in this? Because this is about hypothesis testing. In the hypothesis testing, sometimes we have to find the value that corresponding to, like, so the area in the upper tail and lower tail here corresponding to the area, but like it's the probability of happening is very, very small. Okay, like if you want, like in the last example, 2.5%, so that the probability of happening is only 2.5%. Again, the probability of happening here is also like 2.5%. So in hypothesis testing, we want to set a certain criteria for reject some hypothesis. If this hypothesis is true, but the chance of happening is only 2.5%, maybe we have to reject the null hypothesis, for example, right? So usually we set the area here to be like 10%, 5%, 2.5%, or even 1% in some cases. The idea is that, let's say that if you have a hypothesis that the probability of being struck by lightning is 0.00082%, so less than 1%, but then you go out with your friends in Songkran and you observe that 2 of your friends got struck by lightning, right? So if the hypothesis is true and the probability of lightning struck is less than 1%, but you see 2 of your friends got struck by lightning with your own eyes, right? So you might think like, am I observing an event that have less than 1% to happening, or in fact, this hypothesis is wrong. In fact, that the probability of people being struck by lightning is higher than that. So this is like what we do in hypothesis testing, and it will be in step 2. Okay, so you don't have to worry about it now. Okay, so the last handout is just exercise, right? To find the SAT. So the first 2 is to look in the table and find a probability from the table. What is the probability of SAT less than 1.61, right? The last one is to calculate the probability. Again, you have to, know the mean of 1,000, SD of 2050, and then you have to convert that into, what do you want to know? You want to know what is the probability of Y lying between 800 and 1,100. So you have to convert that interval into SAT, and then you can look up that in the table, okay? So you can go and work it out, and maybe next Wednesday, we can talk about this, okay? Anyway, that's it for today. I'll see you next